This is Babitha, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering. Today I am going to discuss about problems related to rectifiers. That is nothing but the problems in the half-wave rectifier, center-tapped full-wave rectifier, as well as in the bridge rectifier. So while coming to the contents, just I'll revise what is meant by rectifier and why we are using this particular rectifier in the power supplies, and we will discuss about what is meant by all the types of rectifiers, and also we will discuss the problems related to all the types of rectifiers. So here, while coming to the rectifier, the function of the rectifier here it is to convert the AC signal into DC form. It is nothing but that signal may be the voltage signal or the current signal. So the function of the rectifier is to convert the AC signal into DC signal. Where we require this particular DC signal here? Generally in the power supplies, we will utilize this particular DC signal. So why we require this power supply units here means in order to run any applications, we require the DC voltage here. But from the mains, we will get 230 volts AC supply. From the mains, we will get 230 volts AC supply, but we cannot use this 230 volts supply for our applications. And in order to run that particular applications, we cannot use the 230 volts AC supply directly. So that's why we will apply this 230 volts supply to the step down transformer one first. So this step down transformer will convert the 230 volts to a 15 volts range. So the function of the transformer is to transfer the ratio. It will change it to 230 volts to 15 volts here. After this, we will apply this 15 voltage to rectifier circuit. So the function of the rectifier is to convert the AC signal into the DC form. But even though after performing the rectification operation, we will get some amount of AC signal also along with the DC signal. So that's why the output of the rectifier here it is pulsating DC. Pulsating DC is nothing but DC voltage or current consists of AC ripples or AC signal. So in order to nullify the AC signal which is present in the DC or pulsating DC, we will apply the output of this rectifier to the filter circuit. So the function of the filter is to filter out the AC content. So by using the inductors as well as the capacitor circuits, we can able to rectify the AC signal. So capacitor allows the AC signal and inductor allows the DC signal. So that's why inductor we will connect series to our applications, and the capacitor we will connect shunt to our application or load in order to nullify the AC signal which is coming from the pulsating DC signal. And after filtering, we will get the DC signal. But to run our applications, we have to get the stabilized voltage or without variated. That's nothing but we need to get stable voltage. It should not vary with any parameters. So that's why after filtering, we will apply this signal to the regulator circuit. So the function of the regulator is to provide the stabilized voltage in spite of any variations in the circuit parameters or load resistance or temperature variations. So from the regulator, we will get the constant DC voltage. So this particular constant DC voltage we can utilize for our applications. So in this particular power supply unit, we are going to utilize the rectifier. So these rectifiers are of three types. There is half wave rectifier, full wave rectifier and bridge rectifier. So in the case of half wave rectifier, the name itself indicating when you are applying the input signal to this particular rectifier circuit, it is going to utilize only half cycle of the input signal for the rectification process. So because of that reason, it is named as half wave rectifier here. So the output we will be getting here it as like this. Only for the positive half cycles it will provide the output voltage, and for the negative half cycles it will provide the output as 0 here. And in this case we are going to utilize one the transformer as well as one diode in order to convert the AC signal into DC signal. And while coming to the full wave rectifier, so this full wave rectifier is going to utilize total full cycle of the applied input signal. But the thing is, instead of normal transformer, here we utilized the center tapped transformer. So what is the difference between this normal transformer and the center tapped transformer? Here it is. In the case of center tapped transformer, in the secondary winding, we will provide one tapping at the center of the secondary winding. So that will separate the secondary winding into two windings. So here what is applied voltage from the primary, that it will appear here it as Vm here and one more Vm here. Suppose here it is positive means positive to ground, and here it is negative means negative to ground. Why? Because this center tapping wire is grounding here. So that's why positive voltage will go here and negative voltage will come to the second winding of the secondary winding. So during the first half cycle, one diode will conduct, and during the negative half cycle, one more diode will conduct. So overall, during the positive half cycle as well as during the negative half cycle, we will get the output as V maximum, how much input voltage we are applying, that much we will get across the output here. So because of this reason, this rectifier we can call it as the full wave rectifier. Why? Because it is going to utilize the total full cycle of the input signal for the rectification process. And well, coming to the bridge rectifier. Actually, this full wave rectifier as well as bridge rectifier both coming under the full wave rectifiers only. The basic difference between this rectifier and bridge rectifier here it is. In the case of full wave rectifier, we are using the center tapped transformer and two diodes. But in the case of bridge rectifier, instead of center tapped transformer, we are using normal step down transformer, and instead of two diodes, we will use four diodes. That is nothing but at a time two diodes are going to conduct here, and for one half cycle two diodes will conduct, and one more half cycle two more diodes will conduct, and the two particular diodes will operate in series so that the function of both the rectifiers are similar here. But in the construction wise, there is a difference between both the rectifiers, but in the analysis wise as well as in the output voltage, there is no difference between both the rectifiers. Only few parameters will vary between the two rectifiers here, that we will see in the analysis part. This and all we discussed in the rectifier session. In the analysis part, we are going to find about the how much DC current we are getting from the rectifier circuit and how much DC voltage we are getting. And we told already, in the case of rectifier or from the output of the rectifier, we are getting DC as well as AC signal. So these DC signals we have calculated output voltage as well as output current. So along with this we are getting the AC voltage. That AC voltage or current we are representing here with the RMS current or RMS voltage here. And next, efficiency of the rectifier, how much efficiency it is providing. Generally, we will design any device to achieve 100% efficiency, but because of any practical reasons, we may not reach this particular 100% efficiency here. But in the case of half wave rectifier, it is going to provide very less efficiency, almost in 40% range only. And next one is ripple factor. So ripple factor will indicate how much AC content which is present along with the DC output. And regulation is for stabilizing the voltage. And transformer utilization factor, this will indicates how much secondary voltage is utilizing for rectification operation. And peak inverse voltage indicates when the diode is in reverse bias condition, how much voltage we are getting across the output, that will indicate the peak inverse voltage. And this peak inverse voltage is applicable for all the kinds of rectifiers, that may be half wave rectifier, center tapped rectifier, or bridge rectifier. And form factor, peak factor will indicate the maximum values as well as the average values of the signal. So here first we will revise the half wave rectifier formulas, then we'll go with the problems. So the first parameter we are going to calculate in the half wave rectifier is the maximum current. We will represent here it as Im, and the maximum current we can calculate from the maximum peak voltage Vm divided by the total resistances which are present in the half wave rectifier. In the half wave rectifier we are having the transformer and one diode and one load resistor Rn. So here we will apply 230 volts supply. So why we are considering RF as well as RL in order to calculate Im here means, here RF is nothing but the forward resistance of the diode and RL is nothing but the load resistance of this circuit. So in this particular half wave rectifier we are having only two resistances. So that's why in order to calculate the maximum current we are taking the maximum peak value of the input voltage, that is Vm, divided by total resistances in the circuit. Those are RF plus RL. In some cases, we can also get RS, that is the secondary winding resistance. So if the secondary winding resistance also we are taking into consideration, in that case we will get Im equal to Vm by sum of RF plus RS plus R. So this is depends upon the given parameters. We need to consider the resistors here. Definitely in all the half wave rectifiers we will be having the RF as well as RN, but RS if it is given in the problem we have to consider, otherwise we should not consider the RS in the form. And next, average or DC current we will represent with IDC. That value is IDC equal to Vm by pi into RF plus RN. And in this case, suppose RL is far greater than RF, definitely the load resistance value is very high compared to the forward resistance of the diode. When the diode is in the forward bias condition, the resistance value is very less. But when the diode is in the reverse bias condition, the reverse resistance is very high. But here we are considering the conducting state of the diode. So that's why forward resistance we are taking into consideration. And that particular forward resistance is very less compared to the load resistance. So in that particular case, the IDC is approximated here it as Vm by pi into RL. Why? Because we are neglecting the RF value here. Vm by pi into RL. So here 1 by pi value is 0.318 into Vm by RL is the IDC formula. And next one is how much DC output voltage we are getting. We are indicating with VDC here. It is Vm by pi is equal to 0.318 into Vm. So IDC is Im by pi and VDC is equal to Vm by pi in the case of half wave rectifier. And similarly, RMS voltage across the load is VRMS, that is Vm by 2. That is half of the maximum applied input voltage. And next one is efficiency of the rectifier. That is the ratio of DC output power to the AC input power of the rectifier here. That we will represent here it as PDC by PAC here. It is the ratio of PDC by PAC. So this PDC value we can write in terms of current as well as voltage here. So here I have taken in terms of current. So that's why DC power is IDC square into RL and PAC is IRMS square into RF plus RA. And we can also write it as PDC by PAC is equal to VDC square into RL by VRMS square into RF plus RL. So in order to find the efficiency of the half wave rectifier, we can utilize this particular formula as well as this particular formula here. And next, ripple factor. So ripple factor will indicates how much AC component which is present in the voltage or current when we are calculating the average or DC value of the signal. So that we can calculate here it as ratio of RMS value of AC component divided by DC value of the output signal, that is VRMS by VDC. So this particular VRMS by VDC we can calculate as ripple factor gamma equal to under root of VRMS square minus VDC square by VDC. So here VRMS value is VRMS square minus VDC square. If you want to find the root mean square value, we have to make it as under root. Otherwise, directly it is VRMS minus VDC only divided by VDC. So VRMS by VDC whole square minus 1, that is the ripple factor formula in the half wave rectifier. And next one is transformer utilization factor. Actually, transformer utilization factor indicates how much secondary voltage is utilizing for conversion of AC to DC in the half wave rectifier. That we can calculate from the how much DC power is delivering to the load divided by how much AC rating of the transformer secondary. So here DC power we can write in terms of IDC square into RL. IDC value we got here it as Im by pi. So that's why we took it as Im by pi whole square into RL divided by AC rating of the transformer is nothing but how much AC voltage which is flowing in the secondary of the transformer as well as how much AC current or RMS current which is flowing in the secondary winding of the transformer. So the multiplication of that RMS values of voltage and current will give the AC rating of the transformer. And peak inverse voltage in the case of half wave rectifier is Vm. Why it is Vm means in the case of half wave rectifier, we are going to utilize the single diode. So when you are applying the negative half cycle, to your diode, in that case diode is in the off state. But how much voltage which is appearing here, it is nothing but Vm value. So that's why peak inverse voltage is Vm. And the form factor. The next parameter is form factor, which is defined as the ratio of RMS value to the average value. It is denoted by F. That is, in terms of voltage as well as current, we can take it as, if we calculate this, we will get it as 1.57 theoretically. And the peak factor is defined as the peak value to the RMS value. In the half wave rectifier, theoretically we will get it as 2. So we will see one problem in the case of half wave rectifier. So in the given problem is a half wave rectifier having a resistive load of, that is nothing but RL value is equal to 1000 ohms, rectifies an alternating voltage of, that is nothing but primary voltage 325 ohms peak value, and the diode has a forward resistance of, that is RF, equal to 100 ohms. Find peak, average and RMS values of current. Peak value is nothing but maximum value of the current, and average value is nothing but IDC current, and RMS value is nothing but IRMS. This is the first bit, and in the second bit we need to calculate DC power, how much DC power we are going to get in this particular rectifier, and third one is PAC, how much AC power, and fourth one is how much efficiency we are getting from this particular rectifier. So here they given the load resistance value as well as peak value of the voltage directly they have given, that is nothing but VM 325 volts, and the forward resistance of the rectifier also given. We need to find all the currents as well as powers and efficiency from the given parameters. So here first thing we need to calculate, here it is maximum current IM. So the formula for this is VM by RF plus RL. So VM value already given, that is 325 volts, divided by RF value is 100 ohms plus RL value is 1000 ohms. If we simplify this, we will get it as 0.295 amperes. And similarly, we need to find the IDC value. IDC in the case of half-wave rectifier is IM by pi. IM value is 0.295 divided by pi value is 3.14. So if we simplify this, we will get it as 0.094 amperes. And next parameter we need to calculate, here it is IRMS. IRMS is equal to IM by 2, that is equal to 0.295 divided by 2, that is 0.047 amperes. So we have calculated all the maximum, average as well as RMS currents. And the next parameter we need to calculate, here it is PDC. DC power, how much DC power delivering to the load, that we can calculate from the IDC square into RL. That is nothing but we have already calculated the IDC value, that is 0.094 whole square into RL value is 1000 ohms. If we simplify this, we will get the DC power as 8.836 watts. So this is the DC power. And next we need to calculate the AC power, how much AC power coming from the secondary of the transformer, that we can calculate from the IRMS square into RF plus RL. So IRMS value we got here it as 0.047 whole square into RF is 100 plus RL is 1000 ohms. So if we simplify this one, we will get it as 2.4299 watts. So AC power, this much is delivering to the circuit. And next we need to calculate the parameter efficiency, that is DC power to the AC power. So PDC we got it as 8.836 and the AC power 2.4299. So the efficiency we will be getting here it as 36.36%. Generally, in the half-wave rectifier, theoretically we will get 40.6%, but practically we may not reach this particular value. So that's why in this particular given problem, or from the given parameters, we got the efficiency as 36.36%. And the next problem is about half wave rectifier only. So in this, the given a voltage of 200 cos omega t is applied to the half wave rectifier with a load resistance of 5 kilo ohms. Find the maximum DC current component and RMS current, ripple factor, transformer utilization factor, as well as rectifier efficiency. So here first we will write the given values. Here directly they given it as 200 cos omega t is nothing but Vm cos omega t. So they given directly Vm value as 200. And the load resistance RL is 5 kilo ohms. We need to find the DC current as well as RMS current and ripple factor, transformer utilization factor, as well as efficiency. So the first parameter we need to calculate here it as the maximum current. Why? Because to calculate the average current as well as RMS current, we require the maximum value of the current. So the maximum value of the current Im is equal to Vm by RL only here. Why? Because they didn't mention any forward resistance of the diode also. Only they given the load resistance value. So that's why Vm is equal to 200 here and RL is 5 kilo ohms. So this value we will get it as 0.04 amperes. And next we need to calculate the DC current. IDC equal to Im by pi in the case of half wave rectifier. So Im value here it is 0.04 divided by pi value is 3.14. If we simplify this, we will get it as 0.012 amperes. That is the DC current. And next we need to calculate RMS current, IRMS. So IRMS current is equal to Im by 2. So Im value we got here it as 0.04 divided by 2. That is 0.02 amperes. So IRMS value is 0.02 amperes here. And next we need to calculate the ripple factor. So the ripple factor we can calculate here it as IRMS by IDC whole square minus 1. So here we have RMS value as well as IDC value. RMS value is 0.02 divided by IDC value is 0.012. So if we simplify this one, we will get it as 0.57. So ripple factor from the given parameters is 0.57 here. So next we need to calculate the transformer utilization factor. So the transformer utilization factor is nothing but PDC by PAC rated. That is nothing but PDC. We can write it as IDC square into RL. This one is Vm by root 2 into Im by 2. So if we substitute all these values here, so IDC value is 0.012 whole square into load resistance is 5 kilo ohms, that is 5 into 10 power 3 divided by Vm value is 200 divided by root 2 into Im value we got here it as 0.04. 0.04 divided by 2. So after simplification, we will get it as 0.284. So the transformer utilization factor is 0.284. And next we need to calculate the efficiency of the rectifier, that is PDC by PAC. So to calculate PDC, I'm taking here it as IDC square into RL. That is nothing but IDC value is 0.012 whole square into RL is 5 into 10 power 3. So if we calculate this, we will get PDC value. And next, we need to calculate PAC. PAC value is IRMS square into RL only. Here also they didn't mention any RF, so that's why IRMS into RL. That is nothing but RMS value. We got here it as 0.02 whole square into 5 into 10 cube. We will get PAC. So to find the efficiency, substitute the PDC value as well as PAC value, so that we will get the efficiency as 40.25% from the given parameters. So this and all we have calculated for the half wave rectifier. So these are the answers I have mentioned here for the reference and the answers. And next one is, till now we have discussed about the problems related to the half wave rectifier. So next we will see the full wave rectifier formula, then we'll go with the problems of full wave rectifier. So the maximum current Im in the full wave rectifier is again similar to the half wave rectifier, that is Vm by all the resistances which are present in the rectifier, that is secondary winding resistance Rf, forward resistance of the diode as well as the load resistance. And the average current IDC is 2 Vm by pi into Rs plus Rf plus RL here. So if RL value is far greater than sum of the Rs and Rf here, then we can write it as 2 Vm by pi RL or else 2 Im by pi. IDC equal to 2 Im by pi. And next one is output voltage or VDC is 2 Vm by pi. And RMS voltage across load is Vm by root 2. And IRMS current is Im by root 2. And the efficiency is defined as the DC power delivered to the load by AC input power from the transformer secondary. So PAC by PDC. And the formulas of PDC and PAC is IDC square into RL divided by IRMS square into RF plus RS plus R. And the ripple factor is, we can calculate here it as ratio of RMS value of AC component to the DC value of the signal, that is VR RMS by VDC. After simplification, we will get it as under root of VRMS by VDC whole square minus 1. And next one is transformer utilization factor. It is defined as how much DC power delivered to the load divided by how much AC rating from the transformer secondary. And the peak inverse voltage in the case of a center taper transformer is 2 Vm. Why? Because each and every half cycle one diode is in the off condition, so that's why two diodes are present, so that's why Vm plus Vm is 2 Vm here. And the form factor is the ratio of RMS value to the average value, that is nothing but AC value to DC value. And peak factor is, it is the ratio of peak value to the RMS voltage. And peak to peak ripple voltage is EDC by 2 FCRL in the case of full wave rectifier. And the ripple factor, when we use the capacitor filter, in that case we will get it as 1 by 4 root 3 FC into RL. So next we will see the problem related to the full wave rectifier here. So these are the answers I have given for reference. A full wave rectifier has a center taper transformer 100 volts. Each one of the diode is rated at I maximum of 400 milliamps and I average of 150 milliamps. So here they given the primary voltage as 100 volts, okay, and I maximum value equal to 400 milliamps and I average value is 150 milliamps. And neglecting the voltage drop across the diodes, solve. The first we have to calculate the load resistance and DC voltage as well as DC current and peak inverse voltage of the circuit. So the first thing is we need to calculate the secondary voltage, how much we are getting, and after that we need to calculate the maximum peak voltage. Then we can able to find all the asked parameters in the given problem. So to find the secondary winding voltage, that is VSM, we have to take it as 100 into root 2. 100 is the primary voltage is given. Why? Because VRMS is equal to Vm by root 2. So to find the Vm value, we have to take root 2 into VRMS. So this is the RMS voltage given here. So if we find this V secondary voltage, we will get it as 141.42. And next we need to find the maximum voltage. So here, because of the center tap transformer, this is the secondary maximum voltage. But in the case of secondary center tap transformer, in the secondary winding, the winding is divided into two halves. So that's why to find the Vm, we have to take VSM by 2, that is 141.42 divided by 2. We will get it as 70.71 ohms. This is the maximum voltage. And next we need to calculate the DC current or RL resistance value. VDC current in the full wave rectifier is 2 Vm by pi. That is 2 into 70.71 divided by 3.14. After simplification, we will get it as 45.03 volts. This is the DC voltage from the given parameters, and the maximum voltage is 70.71 volts. And next we need to calculate the IDC value. So IDC from the given average value of the current we can calculate. So IDC is equal to 2 into I average. Why? Because we are using two diodes. That is 2 into 150 equal to 300 amperes. That is the IDC current here. But here we require the RL value. So to find the RL value, again I am taking Vm by RF plus RL and IDC equal to 2Im by pi. So here in this particular equation, if you substitute all the values here, we know the Im value, Vm value, as well as RF resistance is not given. So don't consider that. We will get it as Im by Vm by RL. So from this we can calculate Vm by Im, that will give the load resistance value. So that load resistance value is 0.15 ohms. So next we need to find the peak inverse voltage. So peak inverse voltage is nothing but, in the center tapped full wave rectifier, peak inverse voltage is 2 Vm. That is nothing but 2 into 70.17. That is 141.2. Peak inverse voltage is 141.2 ohms. poles. So in this way, we need to calculate the parameters in the full wave rectifier. And the next problem related to the bridge rectifier. Till now we have discussed about the center tap transformer problem. So now we will see the bridge rectifier problem here. So a bridge rectifier uses 4 identical diodes having forward resistance of 5 ohms each. So the given forward resistance is 5 ohms in each diode, and the transformer secondary resistance, that is nothing but RS, is equal to 5 ohms, and the secondary voltage Vs is equal to 30 V RMS. And here, in order to determine the DC output voltage VDC for IDC equal to 200 milliamps, and we have to find the ripple voltage VR RMS is equal to how much. So here first we need to find the IM value to find the VDC value. So to find IM, first we require VM here. They given it as 30 VRMS. It is nothing but 30 into root 2. So we will get the maximum voltage as some parameter we will get here. And to find the IM value, we have to take it as VM by RF plus RS. RF plus RS value, if we substitute the VM 5 plus 5, we will get it as IM value. So after finding the IM value, next we need to find the VDC. VDC is nothing but, here it is, 2 VM by 5. But from the, so VM value, how much we will get, substitute the VM value, and pi value is 3.14. So that we will get the VDC value here. We'll get the VDC value as 24 ohms. And next we need to find the value of VR RMS. VR RMS means we have to take VDC minus V RMS to find the value of this one. I'm very sorry, we have to take VRMS minus VDC. So VDC value we know here. To find the VRMS, we have the formula, that is VM by root 2. If you substitute this value, we will get it as VRMS voltage. So after finding the VRMS voltage, we can find VRMS is equal to VRMS minus VDC voltage, that is 24 ohms. If we substitute VRMS as well as difference of 24, we will get it as VRMS voltage. So in this way we can able to find all the values of given parameters. We have calculated the maximum current IM as well as the load resistance and VDC voltage as well as VR RMS voltage, triple voltage here. And to find the load resistance value, again you can utilize here it as IDC VDC by RA. So here we know the IDC as well as VDC value. You can calculate RA value easily. So here these parameters are answers I have given here for reference. So in this particular session, we discussed problems related to the half wave rectifier, center tapped rectifier as well as bridge rectifier. So in order to solve the problems in any kind of rectifier, we have to analyze the rectifiers first, and we need to get the formulas from the analysis so that we can able to easily find any parameter from the given problems. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.